So today we're gonna continue our discussion of additional angular momentum, part 2. This is lecture 27. We're gonna have a total of 30 lectures. So review of what we discussed last time. I'll probably need to use the board a lot today, so I don't know, it's not the best board. Hopefully my handwriting is not the best either. So please do ask questions, something not readable. Okay, so what we discussed last time was we said consider two spin half particles. The particle 1 has the spin vector S1. Particle 2 has spin vector S2, and then we can sum them and call this the total spin. Of course, as we discussed it before, because this is a composite system, the Hilbert space is a tensor product of the Hilbert space of the two. And the operator S1 is nothing but S tensor identity on the second one, and S2 is identity on the first one, tensor S on the second. Now, hopefully it's clear that operators that are supported on the first guy and the second guy commute. Is that clear? But the operators on the first, of course, satisfy a copy of the spin half algebra, Lie algebra of SU2, and the second one similarly satisfy the Lie algebra of SU2. These relations are called the Lie algebra. Just I know that I have not defined it, but these are called Lie algebras. Lie as in Lie. All right, two options for bases. We talked about there is the first spin basis, which is basically the spin basis of the first guy, tensor the spin basis of the second one. These are the eigenkets. These are simultaneous eigenkets of S1Z, S2Z, S1 squared, and S2 squared. It's pretty clear to see, well, S1Z clearly commutes with this guy commutes with this guy, and everything on 1 and 2, they commute. We use this shorthand notation, plus minus. I'm sticking with that because it's Zacharias notation. Just a little warning, it's not the most common notation. People usually use ket 0, ket 1. Anyway, so in this basis, here are these are the basis vectors, plus, minus, plus, minus. Then there's a second basis. This is the basis that the eigenkets of them. Sorry, the basis is defined by its vector elements, which are the simultaneous eigenkets of still the same two operators. So S1, 2, and S2, 2, but also S2 and SZ. So SZ is the total spin up, and S2 is S1 vector plus S2 vector squared, right? So we discussed this, right? So what is important here is that when you write S1 plus S2 squared, means the inner product, right? And this we wrote as S12 plus S22 plus 2 S1Z, S2Z plus S1 plus S2 minus plus S1 minus S2 plus, right? All right, so what are the eigenvalues? Hopefully it's clear what the eigenvalues are in this case. Well, yeah, hopefully that's clear. Good. So what we did do is we found that the second basis was perhaps less familiar to you guys. So we worked out the basis elements. The matrix, there was one ket, which we called it the singlet. This is the state which has 0 S for the total spin. So it has net spin 0. And of course, it can't have M. This we call the singlet state. And then the other three are called the triplets. Plus, this is the same eigenket we had before, minus. These are spin 1, total spin. And then there was a total spin 1, M equals 0, which is this entangled state, this bell pair. Now, the coefficients that appear as we go from the one basis to the other are called the Clebsch-Gordon coefficients, right? So we did not here are what they are. Here you see, for example, this is a Clebsch-Gordon coefficient, this is a Clebsch-Gordon coefficient. At the moment, I have not given you a sharp definition, but today I will give you a sharp definition and a particular convention. There are a bunch of conventions. Any questions about this? Yeah.
So I guess what does this mean in the context of like their composites like
right?
It seems like it could be a variety of different little spins like
yeah. So what it is something like this. I tried to give an example of that. Maybe I didn't, but next lecture I'll actually give you some physics context to this. Imagine you have a whole bunch of silver atoms. Each silver atom has this spin half degree of freedom. If you have a very good measurement device, you could individually measure them, and it's natural to talk about this basis of ket M1 and sort of ket M2, blah, blah, blah. This is a natural basis. But if you have a measurement device, that is basically this. It takes 10 atoms and the way we measure spin is exposing it to a magnetic field. And you expose the 10 atoms together. You cannot resolve them well to just some magnetic field, and then you see some total spin. Now the eigenkets that are relevant for you, because you cannot resolve individual atoms, are these total spin eigenkets. Right? Very good question. Any other questions? All right. Now, today what we're going to do is we're going to discuss the formal theory of angular momentum. So I'll just describe very, very formally how the theory of angular momentum works. And as I said, there will be a lot of calculations, but I cannot do everything. So part of it is pushed to a homework problem. All right. So imagine you have two angular momenta operate. So actually, one notation that I don't know if this is helpful or not, but it's convention that terminology that Sakurai uses. Sakurai refers to spin as spin angular momentum. It's kind of weird to call it that way, but to contrast it with orbital angular momentum. So that when Sakurai wants to say, when they talk about angular momentum, total angular momentum, to the sum of the orbital angular momentum plus spin angular. That's the advantage of this terminology, okay? So here, when I say spin or J, this could be angular momentum, orbital, or spin angular momentum, right? So what you have is two of such angular momenta, spin or orbital, and you want to add them. Okay, so we said that if these are corresponding to different, oh, I forgot to, remind me to include the discussion of direct sum at some point later in the course. I don't have it today. Maybe if I have time at the end, I'll discuss it. So here we're gonna represent it as a tensor product, of course. And the Hilbert space of because it's a tensor product, the Hilbert space of 1 is 2J1 plus 1 dimensional. Because this is spin J. 1. The Hilbert space is 2J2 plus 1 dimensional. That's the Hilbert space. Here are the commutation relations. So far, is the setup clear? What we're going to discuss. So we have a spin J 1 particle and a spin J2 particle. All right, we talked about representations. The action of a rotation would be representation of rotation on the first one, tensor representation of rotation on the second one. So if you rotate around n hat, unit vector n hat by angle phi, this is the way you would represent it. J1 and J2 are, of course, these guys, right? J1 and J2. Now, there's also the total J operator. I understand that the notation can get confusing, especially if J1 dot looks like Ji, but but this is the total angular momentum as opposed to J1 and J2, right? So good. So be careful with the notation. These are the generators for the of rotations for the entire system. Now there are two choices of bases. The first choice is J1, J2, M1, M2. These are the simultaneous eigenkets of J1 squared, J2 squared, J1z, and J2z. Right? Here are the eigenkets. So I'm going to make a suggestion. Well, okay. Is that clear, right? So what it is just what these kets are is J1, M1 tensor, J2, M2 that we're writing as J1, J2, M1, M2. Good. Now, the second basis is going to be, or are going to be the simultaneous eigenkets of what operators?
J squared.
J squared, JZ, total JZ. And then what are the other operators? Exactly. J1 squared and J2 squared. So here we have J1 squared, J2 squared, J1z, J2z. So the thing that has changed, this part is the same. So in the second basis, we're going to have J1 and J2 as well. Right? But then they're going to be a total J eigenket of this and a total M eigenket of this. For this reason, that the two bases have J1, J2 in common, you could simplify your notation, just don't write it. Your equations look a lot easier. Sakurai keeps all these J1, J2s everywhere. At some point, I'll drop them just so that they fit in one page. Okay? So is it clear? Because both bases take J1 squared and J2 squared as, well, they're both the eigenkets of these guys. So even though you can label them, you should label them because these are good quantum numbers. But because when we're talking about Clebsch-Gordon coefficients, going from this basis to that basis, nothing happens to these bases. Right? In this notation, the example of two spinners we talked about, let me write it here. The two spinner example we talked about looks like this. The first basis is S1 equal half, M1 tensor, S2 equal half, M2. So you could write it as, J1, J2. So you could write this as J1 equal half, J2 equal half, M1, M2. We didn't do this, we didn't write this part, it was clear, we knew it, right? And then the second basis is going to be J1 equal half, J2 equal half, but then J was sometimes 1, sometimes 0, J and N, right? J, so we have these things. We just talked about this part of it, let's suppress that notation, this part, let's suppress that notation. It just repeats. Good. All right, here's option B, as I said. You notice that, of course, there are the simultaneous eigenkets of J1, J2, so J1 and J2 are going to be used. But now, the only thing that's changed, we've gone from M1, M2 to JMs. Right? These are the eigenkets of the total angular momenta. Any questions? I just want to remind you guys that the reason that these bases are different is that, so let's just write down what the operators are. That, so option A, the operators that we're looking at the simultaneous eigenkets of them were these. option B, where J12, J22, J2, and JZ. Now, notice that this commutes with these two guys, but this one doesn't. So it's all about this, the total spin. All right, so what are the Clebsch-Gordon coefficients? Take this ket Jm, insert as a resolution of identity and option A basis. What do you obtain? You obtain a sum over, well, you obtain a matrix acting on M12, giving you the Jm basis. These are called the Clebsch-Gordon coefficients, and hopefully it's clear that this is the unitary that rotates M12 basis to Jm basis. So it rotates the spin of option A to option B. These are called the Clebsch-Gordon coefficients with this convention. You might talk about the basis that goes the opposite in the opposite direction. Sometimes people, depending on your convention, call those Clebsch-Gordon coefficients as well. But doesn't matter. You just write down these numbers. Numbers are pretty clear. We listed some of the properties of these. We said that, oops. Oh no. Did I go over? Yeah, I went over the properties of Clebsch-Gordon coefficient. I did not. Oh, whoops. Okay, so good. I'm going over them now. So first thing to notice is that the overlap of N1, M2, and Jm, this Clebsch-Gordon coefficient is 0 unless M1 and M2 is equal to M. Is that clear why? Here's a proof of it, but intuitively, is that clear why? Intuitively, it's the following thing. M is M1, sorry, M is the eigenket of Jz, which is J1z plus J2z. These two terms commute, right? Which means that if you had an eigenket of this with M1, an eigenket of this with M2, the result would be an eigenket of this with M1 plus M2. So it's somewhat intuitive. The z components of spins add up. You want to prove? Here's how you would prove it. Well, take J1, take this matrix element, insert in the middle of it Jz minus J1z minus J2z. By definition, this operator is 0, so this should be 0. Now act with Jz on the right and these two terms on the left. These are self-adjoint operators, so Hermitian operators, so you could act on left or right. What you obtain is this. This guy is an eigenket of Jz, so with eigenvalue m, this comes out. These two guys, this is an eigenket of J1z and J2z, so, and the eigenvalues are m1 plus m2. This should be 0. Therefore, m is equal to m1 plus m2. It's only non-zero in those cases. Yes.
Just to clarify, the delta, it says m comma m1 plus m2, or is it m1?
Yeah, no, it is comma. So okay. This is Kronecker delta. Kronecker delta is this. Kronecker delta of x comma y means that it's equal to 1 if x equal to y and 0 otherwise.
Yeah.
Yes. Yeah, my handwriting went up. So that's property number 1. That's very important. I prefer not putting the J1 to J2. It gets confusing for me, but anyway. Are there any questions about property 1? Property 2 is the following fact. Let me just say it in words first. I'm not going to prove it. It requires a little bit of group theory, but I'm going to explain to you guys why intuitively it should hold. All right, just some sanity check, some consistency. When you take a spin degree of freedom J1 and a spin degree of freedom J2, the total spin you could get is anything from absolute value of J1 minus J2 to J1 plus J2. This is the total spin you could obtain. Let's first see what the statement is. Is that good? Yeah.
Just a question about notation, but when you say later that you drop J1 and J2, you mean you just drop the term in the
Yeah. The ket instead of writing J1, J2 every single time, I'll drop it.
Okay, yeah.
So for example, what does this mean for adding two spinners, the example we discussed last time? It means that, so you have your J1 is half, the other J2 is half. So your total spin is going to be anything from 0 to 1. We saw spin 0, singlet, spin 1, states that were triplets. Good? So it matches what you know already. Now, a sanity check. It's just the dimensionality of the Hilbert spaces. Let me do this on the board. You could read it, of course, up there. So when you put together J1, if you have a, well, we talked about the Hilbert space. What is the total dimension of the Hilbert space? If this is this guy is 2J1 plus 1 dimensional, this guy is 2J2 plus 1 dimensional. So that's the total dimension, 2J1 plus 1 times 2J2 plus 1. Now, if this ends up having a whole bunch of options, starting from J1 minus J2, assume that what I just told you is correct, right? And all the options all the way to J1 plus J2. Right? These are all the options that come out. What is the dimensionality of this subspace? Is 2J1 plus J2 plus 1. What's the dimensionality of the next one? This is when J is J1 plus J2 minus 1. This is 2J1 plus J2 minus 1 plus 1. All the way. Down here you have 2J1 minus J2 plus 1. In the case of two spins, what was your total Hilbert space 4-dimensional? There were two options, J equals 0, J equal 1, and J equals 0. 0 was this guy, 1 was this guy. What was the dimensionality of this Hilbert space? 2 times 0 plus 1, 1 was singlet. What was the dimensionality of this? 2 times 1 plus 1, 3, so triplets. The numbers, if you add them up, is 4. So it matches. Here, if you add up from this J1 minus J2 all the way to this, it sums up to J1 plus 1. It sums up to the right dimensionality. So it can't possibly go below this, and it's easy to convince yourself it can't go above this either. Think about why it cannot go above this. You could cook up an argument based on this. All right, is the point clear? This is that previously we said 2 times 2 is equal to 3 plus 1. This is saying 2J1 plus 1 times 2J2 plus 1 is equal to the sum. This is an important concept. Quantum mechanics, perhaps one of the most important concepts that we're dealing with here. All right, any questions? Am I going too fast? Have I lost you guys? No? Yes? A little bit. So I will slow down a little bit. Another thing that I can prove, but again, I don't want to drag you guys into group theory. You could always read about this. I don't think that Sakurai has a discussion of this or explanation of this, but By convention, we take the Clebsch-Gordon coefficient to be real. We can do that. Now, that's what I'm not. There's enough freedom to pick the coefficients to be all real. I've not explained that, but just accept it. Now, the matrix of Clebsch-Gordon coefficients, what kind of matrix is it? It's a change of basis. What kind of matrix is it? Unitary. Good. So, what is the defining equation of a unitary? U dagger equals U dagger U equal identity. Right? What is U dagger? U dagger is U transpose, and you first transpose it, and you take the composite conjugate of every element. Now, if every element is real, the composite conjugation doesn't matter. So U dagger is the same thing as U transpose. Right? So your equation, if you can choose them to be real, ends up being like this. What is such a matrix like this called? Orthogonal. So Clebsch-Gordon coefficients in this convention are orthogonal matrices because they are real. So I'm going to keep this and I'm going to use it to derive two equations. Oh, actually, that's my next slide. Good. All right. So what do these equations mean? So they translate to two equations, the top one and the bottom one. So the left-hand side, the right-hand side is identity. That's identity written in terms of those bases. So the top line is, let me stare at it. Okay, sorry, let me write this down. Write down this equation. So this is U transpose IJ U K I. Sorry, let me use an indices volume. Good. I'm going to use alpha and beta so that you don't confuse them with J. This is the first equation. This equals to identity. I'm going to write down the second equation as well. Actually, no, let me go one by one. All right. Can I simplify this further? Yes, this is the transpose, so I can write it as U beta alpha, sum over alpha is delta gamma beta. Right? Now, what is U beta alpha? These are matrix elements of the Clebsch-Gordon coefficients. So let me just suppress the J1, J2 quickly for you. So this is this matrix element. Actually, which one do I want to do first? Yeah, it's this matrix element. Right? Beta alpha. I'm multiplying it by this matrix element. Notice that the alphas are the same. That's why Jm is Jm. And then this is just identity. Now, the second equation, this equation, if you write it, it ends up being sum over alpha, U of, I'm just going to write it, and you guys have to believe me. Well, use a one-liner, you can derive it yourself. Gamma beta. So now, what happens is that now M1, M2 is the same. Right? And you're multiplying and get identity. So these two equations are just a consequence of the fact that we have real Clebsch-Gordon coefficients. They're not deep statements. If you know what the transformations are, you could always write them down. Okay? They just look fancy or long because there are too many labels. Some of them are just redundant. Any questions? Okay, this is just something for you guys to know. Those of you guys who end up doing, actually, whatever field you end up in, except for astrophysics, you might hear this. Sometimes when people talk about Clebsch-Gordon coefficients, people might call them something else. Sometimes they use this notation of this curly thing, this notation. These are called Wigner's 3J symbols. Wigner came up with a lot of this stuff, and he did not use the Ket-Bra notation of Dirac. And this is a notation that is commonly used in math. There's a long story of group theory behind it. This is not news to mathematicians. This is just very, very standard undergraduate level group theory. But we're physicists, we're learning it in the context of physics, right? Sometimes people write them this way. So if you hear anywhere, you hear the words 3J symbols, what it means to you as a physicist is that these are some sort of Clebsch-Gordon coefficients. Yeah.
What's 6J symbol?
Oh, 6J symbol is a fancier thing. It's well, let's not discuss it. I'm happy to tell you more about it. Yeah, I'm happy to tell you more about it. There's something called 6J symbols that we just heard. There is that's related to associativity. So you have groups, you have fancier structures, half algebras, blah blah blah. Yeah. But all of this was discovered by mathematicians, knowing nothing about quantum mechanics. I mean, yeah, that's just a theme of physics. Mathematics is unreasonably useful in describing nature. All right. All right, okay. Now here is something I want to ask you guys. How? So now I'm gonna derive a recursion relation for Clebsch-Gordon coefficients. I understand that it's going to be a lot of indices and somewhat of a complicated calculation. I'll do an example for you, okay? But I want you to ask questions. I don't want you to get lost, because if you open the book and try to read it, in my opinion, it's harder to read the book. I'll try to simplify it as much as I can. So if there are questions, do ask. All right? I think the equations are really ugly because I try to stay close to the notation of Sakurai, but I would have dropped all these kits, J1, J2s from the kits to make them a little bit more compact. But just first, because so I write it this way so that you can compare the text. Okay, so what is the idea? The idea is this. How do you, when I wrote down the singlet state and triplet states, I just wrote them on the board and I said, oh, let's check that these are the eigenkets, and they were the eigenkets. But if you don't know that, it's a more complicated setup. How do you derive the Clebsch-Gordon coefficients? How do you write them down? Right? So, rule of thumb is this. Anytime in physics, you have an algebraic structure where you had a raising operator and a lowering operator, the matrix elements of your raising and lowering operators repeatedly applied are going to be what you're going to use to derive everything. That's the goal. That's the raison d'etre of raising lowering operators. You use them to derive all sorts of relation between things. So if you don't know anything about how to approach a problem, it's just a good guess to take the raising or lowering operators and apply it on the kits. Good? All right. Let me see. I'm not going to do this on the board. Okay, so what are we going to do? We're going to take the ket JM. I'm not going to mention J1, J2 all the time. And act on it with the total raising lowering operators. Total raising lowering operators. The total raising lowering operator is nothing but the sum of the two raising lowering operators. Everybody's with me so far? The other thing that we have in our arsenal of tools is resolution of identity. So put it in there. Just put a resolution of identity. So what do you find? Well, this is a Clebsch-Gordon coefficient. Leave it as is, right? This is a Clebsch-Gordon coefficient. Now, on the left, this, sorry, let me just say, scroll up a little bit to tell you what the logic is. It's similar to this. You take the ket JM, you act on it with some operator, and then you sandwich it with M1. So we're acting on you're acting on JM with J plus minus, and we're gonna sandwich it with this ket. Right? So let me write down the left-hand side. So this is the left-hand side. And my compact notation is this. This is the left-hand side. So is it clear what we're calculating? How am I calculating this? By inserting a resolution of identity in the middle. This is what I'm doing. So written this way, it's not as confusing. Good. The rest is just okay. That's one thing. Actually, if you want this equation to be very much copy of this equation, it can be. What it is, if I want to do literally that, what I write is the following. I write J plus minus minus J1 plus minus minus J2 plus minus Jm is 0, and I put it in the solution of identity. This becomes what I call left-hand side, the rest I call the right-hand side. Now, what was the logic? You act with these guys on this ket, these bras. You act with these guys and these guys. Hopefully you can reproduce it. It's very straightforward. These equations look ugly. So this comes from the fact that I've applied J plus and Jm. Right? These are those coefficients that come out. These come out because I act with J1 plus and J2 plus minus on the left. Good. So I end up with this equation in my compact notation. Let's pause and ask, does everybody follow how this equation was derived? I took an operator that was 0 and stick it inside these matrix elements, and I put a resolution of identity in the middle. Actually, I don't even need to put a resolution of identity in the middle, but anyway, it's just the way that Sakurai does it, so that you could follow the text. Now, let me explain. So you're going to derive this in as a homework. I just explained it to you, but it's helpful. When J plus minus acts on the right, what does it do? It raises or lowers M. That's why on the right-hand side, you have Jm plus minus 1. Right? And this, of course, is unchanged. When J plus J1 plus J2 plus act on the left, what do they do? One of them raises and lowers M1. The other one raises and lowers M2. There are two terms. So you end up with this structure. And then the coefficients are basically the coefficients that you expect from action of J plus J minus, because they have those funky coefficients. Questions? There are people online. If you have questions as well, please do ask. I don't know if you see the board. I think you do. Okay. Yeah.
Should the bottom line on the right-hand side be inside the square root, should be J2 plus minus M2?
Sorry. Which part? So this line? This line?
Yeah.
Where? What do you?
Inside the square root?
Inside the square root should be?
Should that be J2?
Correct. Thank you. Thanks for the correction. No. Wait. Yes. Correct. Thanks so much. Yeah. You see, if you pay enough attention to it, you can catch my typos. Thanks. This is what happens when you write stuff on a plane. Thanks. Good.
So those two terms are just the right hand side.
Those two terms are.
Or just the right hand side.
Yeah, so these two terms are the right hand. Oops. Yes. So right hand side has two terms. This term, and then I'm calling this the left hand side. Right? Good. Now, something to recall. Pay attention to the fact. So what did we do? We related three different Clebsch-Gordon coefficients. Every term here is a Clebsch-Gordon coefficient. Right? We wrote down a relation that relates three different Clebsch-Gordon coefficients. That's not terribly useful. You cannot recursively solve an equation like that. If you could write down an equation that relates two Clebsch-Gordon coefficients, then you could repeatedly use them and get a recursion relation. So the goal is to start with this, find a configuration where one of the terms vanishes for some logical reason, and then repeatedly use it. How could I arrange for a setup like that for one of the terms to vanish? How would, when is the case that one of these, you know that one of the terms vanishes?
Sum isn't equal to the total.
That you could, no, that is, okay. I'll explain in a second.
M1 equaling J1.
Exactly. So you see, I use this super compact notation where I just drop M1, J1 and J2. But of course you can't raise M1 or lower M1 arbitrarily. At some point you're going to reach either minus J1 or plus J1. Recall, this is exactly analogous to what we did in simple harmonic oscillator. We said, let's apply this A or A dagger, in that case A, until we hit 0. We're going to start from there and then recursively apply, construct all the states, right? So you find a configuration where applying further will give you a 0, kills one of the terms, right? And then you repeat it. Let me draw this. It's in the textbook. It's not on my, I think it's a good moment to say it. Imagine the M1, M2 plane. So these are M1s and these are M2s, right? So M1 and M2 here, you start from minus J, minus J1, minus J plus 1, go all the way to, well, if it's integer or half integer, you might skip the center or not, and all the way to J1. Here you start from J2 all the way to minus J2, right? So roughly speaking, there is a block like this. Now, it's actually not a block, and these corners are not allowed, but it's okay, it doesn't matter. What you would start is you would start on the edge of a piece, and you recursively apply these equations. But this is just a comment for you for now. We're going to do that in an example. So recall that the Clebsch-Gordon coefficients are 0 unless M1, whatever sits here, plus this guy is equal to this. Right? Therefore, your terms are only relevant when you have this condition. You have to keep this condition in mind. So there is a way to understand, there was a question about when this is not true. There's a way to understand sitting on the edge in terms of what you said. But I wanted to pitch it this way because that's closer to what we would read in the book. And I think it's also easier to understand, but all right. Any questions? So consider this M1, M2 plane. Let's say you're somewhere here. Okay? What you're gonna do is stare at this equation. The left-hand side is where M1, M2 is. This is the left-hand side. So you're at a point on this plot. Right? Then if you apply J plus, you make a relation between M1, M2, M1 minus 1, M2, and M1, M2 minus 1. So you find a relation between this M1, M2 minus 1 and oops, this guy. Okay, this got turned really ugly. This relation. This relation. You go one of the terms, just let me, here we go. So M1, M2 is left-hand side. On the right-hand side, you have M1 minus 1, M2. You move to the left. And then you have M1, M2 minus 1, you move down. You have two identities. The J plus identity gives you such a relation. So if you want to use the J plus identity, how will you use it? Because it moves you down, you would start down here. It will relate three terms here, but this term is forbidden. This is 0. So now you find a relation between these two guys. And you could repeat it and generate all of this. Good. Now that if you solve for this line, now you could move one line above. You write the triangle equation. Now this is known. So now you could recursively use it. If you want to use the J minus equation, so J minus equation, what it does, let's start it. J minus equation relates M1, M2 to M1 plus 1, M2. So that is moving to the right and then moving up. So this is the triangle you obtain. If you want to use that equation, you start on this edge, right? So this is your left-hand side, your right-hand side are these two terms. And then this term is 0. It's not allowed. So you find a relation here. You repeat this on this line. You solve for all of this. You move one line down, but now you know the third term. This is how completely systematically you solve for Cauchy-Gordon coefficients for general addition of angular momentum. This is the formal theory of angular momentum. Now, what is important at the end, it's the same thing as simple harmonic oscillator. That's why it's so important that you internalize a simple harmonic oscillator as the simplest example in your inside. When you find these recursive relations, what's going to happen is that you're going to write every Cauchy-Gordon coefficient in terms of another one. So fix one, you write everything in terms of that. You still have a normalization condition. We're going to discuss that normalization condition. That normalization condition was also the case for simple harmonic oscillator. If you go back, you'll see it. So we'll discuss that as well. Yes.
I don't think I fully understand why we want one of the terms in the top of the equation.
You have a relation that relates three terms. So if you want to use an equation recursively, you want to find something in terms of another thing, then that in terms of another thing, that in terms of another thing, so you could recursively do it. If you write object A in terms of two things, then in the next step, this one will be written in terms of two things, this one in terms of two things. So the number of options explodes. Okay. You end up with an equation on the left-hand side is equal to many, many terms on the right-hand side. It's not manageable.
So it's just to kind of guide the recursive.
Absolutely. How many of you guys have heard of Gram-Schmidt? Same thing. We're just presenting it differently. There are not a million methods in linear algebra. Good. All right. What I'm gonna do is an example. All right. And I'm gonna work out an explicit example. Let me see. Yeah. Okay. So I might run out of time. Oh my God. But let's do it. Let's do it. If I do it on the board, I was planning on doing it on the board, but I'll definitely run out of time. So let's just do it here. But I'm gonna pause again to ask for questions. Are there any questions? What I'm gonna do is an example. The example I'm going to work at is as easy as it gets. It's the simplest possible example. That's very, very useful. An electron is a spin half particle, right? So it has a spin half. The atom, or sorry, not the atom, the electron could also have orbital angular momentum as it spins around the nucleus of an atom. So now what you could do is an electron that's orbiting a nucleus has both orbital angular momentum and spin angular momentum. There is a net angular momentum. That's what we're going to calculate, right? So we're going to take a spin half particle that has some orbital angular momentum, L. So it's very, the example we're going to work out is very relevant for chemistry, for real world. Is it clear what we're doing? So if my electron has angular momentum L and spin half, it has spin half, what's the dimensionality of the Hilbert space I'm working in?
12 plus 1
Times. Times 2, exactly. The dimensionality of the Hilbert space I'm working in, right? If it's, these are different orbitals of atoms, L equals 0 is the S wave, so I have only 2 states, right? L equal 1, you see how the dimensionality of the Hilbert space works. What are the solutions to these guys, by the way? YLMs. So I can think of this as YLM theta phi for spin up, YLM minus spin down. I'll come back, so I'm jumping in a second. This notation, oh, forget about this notation. I think it's too quick for now. Right, so this is the dimensionality which I'm working with if the angular momentum is up. That's the example we're going to solve. So in comparison to what we're doing, L is J1, J2 is half. L is of course an integer, S is half integer, right? What is M1? We're going to call that ML. What is M2? Is MS either plus or minus 1. What are the allowed values of total? When I write J, is total angular momentum, spin plus orbital. What's the allowed values of the total J? If your electron was S wave means L equals 0 moment. Then J has to be half. There's only one state. Why? Exactly. So if we had this condition that J has to be less than, larger than this, below this. So in the example we're solving, this is L, this is half, right? And then this is L minus half, absolute value, right? L minus half absolute value. If L is equal to 0, there's only one option, J equal half. Whereas if L is larger than 0, there are 2 options, L plus half and L minus half. Good. This is, like for example, L equal 1 for electrons orbiting a nucleus. These are called the P states. So we usually write them as P half, P3 halves, right? That's what the notation is. And I admit, as a high energy theorist, the only time I write these and I never use them. Okay. Good. Is the question clear? What we're trying to accomplish? So what was the method? Let's draw the M1, M2 plane. I'm kind of sort of doing it on the board, but not really. So what is the M1, M2 plane? The M1 plane is ML, and M2 plane is MS. So if you have spin L, you have minus L plus 1 all the way. You will have 0. Why will you have 0? Because L is integer always, right? All the way to L. So this is your M2 or ML, whatever. And then what are the options for MS? Okay, I drew this really poorly. Plus 1 minus, plus half minus half. So what I should have done, being lazy now, is this. This is my axis, M2. These guys up here as well. So these are halves and these are my halves, right? So I have only 2 rows like that. Good. Now I want to use my recursion relations. I had the J minus relation that was relating left hand side. This was the left hand side. These were the right hand sides. And I had the J plus relation. I have to double check. Please double check. This is what I'm not making things up. I think this is what it was. Yep. Okay. It's actually a choice which one you want to use. If you want to use, what am I using here? J minus. Where do you have to start? Top line, exactly. Doesn't matter where actually. On the top line somewhere here. If you use J minus, this is your starting point, and you write an equation. This is the left-hand side. The right-hand side has 2 terms, here and here. But then this term is not allowed, so you only find an equation that relates the Clebsch-Gordon coefficient here to here. We're going to do that in a second. Then what's your next step? Well, this was the J minus. Do the J minus again. This is not allowed. You find an equation that relates the 2. So you now have related these guys. You keep doing this until when? Until you hit L. At that point, when you apply this, none of them are allowed. So you end up, and then you could go backwards as well. So you could have started all the way down here. So you find a relation that relates. Tell me what is it relating to what? You find a relation that relates. I don't know if you do not see it here, so let me just write here. You find a relation that relates. The first relation does this. It relates Jm minus 1. I'm using what? J minus, yeah. To M1 plus 1 and 2 Jm. This is the relation that I'm going to find first. Right? Why is this M minus 1? Because J minus first acts on this guy. Right? And then as I repeat this, I basically recover everything on the top line. Right? So here, this is actually half, right? Because I'm on the top line. All right, so what does the equation look like? Here's what the equation looks like. It turns out that it's helpful to write ML as M minus half. Just a variable here. That's not a random variable. It's not an arbitrary variable. It's M of this guy. But so your relation relates these two guys. Oops, this is not allowed. So this term drops out. So you have an equation that relates M minus half, L plus half, M minus 1. We're working out the case where the total angular momentum is L plus half. What are the options? I just said it. There are only 2 options. There is a choice where J is L plus half, and then there's a choice where J is L minus half. The L is larger than 0. I'm working out the first one. Good? You have to do this for every single one of them, at least at first. Then you realize that, oh, you don't really. You could if you want to. Good? All right. So here's the equation you find. I've just plugged, I've written down to help you guys what these equations are. This is the equation. This is your first equation. You've used horizontally by 1 unit. You keep moving, you repeat this horizontally by more units. Now see what happens. At the second, so the first order term is this. This was the coefficient of the left-hand side, and this was the coefficient of the right-hand side. Well, the other way around. When you repeat this, here you find what you found in the denominator is going to be the numerator of the next order term. So these two guys cancel. So your recursive relations are super neat. If you repeat them, you're going to get this relation. This guy cancels that, these guys cancel that, and at the end, you only end up with this expression. All right, so let's just digest what this expression is. This half is half because that's M2. That means I'm on the second line. This means I'm on the top line. Why is this L? This is M1. It means that I've reached the end of the line here. Right? The coordinate at the end of the line is L, comma, half. Half means upstairs, up here, and L means the end of the line. This is what I started with. And this is what the right-hand side is. Why is the right-hand side this? Because every time you apply a J minus, you're raising this guy as well. Raising, lowering, lowering. Am I applying J minus? I'm applying J minus. You're raising that guy. Yes, you're raising that guy. So this is the relation you find. Is the idea, well, you can work out the details of it for yourself, but is the idea of how this equation was derived clear? You're going to do it in your homework. So I understand that this is a little bit fast, but now if I stare at this coefficient, what is it if my recall what this coefficient is in the context of adding two spins. In the context of adding two spins, I'm just going to write it. I don't know if you don't see the word. I'm going to write it here. It's saying the following. It's saying S equal 1, M equal 1. This is the coefficient in the context of adding two spins. You could know, you start on the top line, and you could no further go to the right. This coefficient, you could take it to be 1. Right? If you recall, if you go back to your equation, you know. Why? Why is this equation 1? Because you could prove that this ket has to be proportional to this. Now, the two vectors are proportional. How could they be different? Up to a phase. But you want these matrices to be real. When I said picking the Clebsch-Gordon coefficients to be real, it means that pick that phase to be 1. Simplify your life. You could have picked a phase here, and then it makes your life complicated. All right, this way, now this term is 1, therefore you found M minus half half, L plus half M. This is what the expression is. Now, you have to repeat this 4 times. Why? Because there are these equations. What are these equations? What are these Clebsch-Gordon coefficients? I started with the case where J was L plus half, but I did say that J could be L minus half as well. So there are the 2 cases. So let's focus on the J plus half. These equations work out the top line. I also have the bottom line. So these give you the bottom line. Then my total angular momentum could be L plus half or L minus half. So I have to repeat that twice for these guys as well. Sounds like a pain. Except that you could do this intelligently. Is it clear why there are 4 sets of such calculations? Because there are 2 possibilities for J, and each possibility for J, you have 2 rows. I now remember. 2 rows. So if you had a higher spin particle, it would be a disaster. It would be so many of them. But now you remember, what are we trying to solve? We're trying to find a unitary rotation matrix that rotates this basis to this basis. Furthermore, we know that we could pick it to be real. So it's an orthogonal matrix. It's a 2 by 2 orthogonal matrix. This is what a 2 by 2 orthogonal matrix is. Can't be anything else. Remember? Therefore, if you know one coefficient, you know all of them. Here was the coefficient you calculated. You copy that here. Then you take 1 square root of 1 minus this thing you calculate. You put it here with a minus sign. Done. Is this step clear? All right, last point, and I did not get to talk about direct sums. I'll try to squeeze in direct sum at the end of next lecture. Do remind me if I forget. I think it's a very crucial thing. I don't want you guys to finish this course not knowing direct sum because nobody really teaches it. All right, very good. So what did we do? We took a spin half particle electron that had angular momentum orbiting the nucleus of an atom, right? And then we looked at the eigenkets of the total angular momentum, orbital from spin, plus spin. And written in terms of the so in this case, what are we writing? We're writing L tensor M, right? Plus minus. These are the eigenkets of the option A, right? So if I pick an N hat, what is this? What did we call this? We call this YLM. Theta and phi, those theta and phi is how you define a hat. So you could think of these guys as 2 vectors, right? So now plus L minus. Good. You want to rotate that using this matrix we just found to the you don't see it. So to the kets that are the eigenkets of total spin. So you multiply this matrix on it, and on the right hand side you get these vectors. These are called the spin angular momentum functions. I apologize for the name. It is what it's called. I did not ask for my opinion when they were designing this. But is the object clear with this? There are 2 of them, right? Because there are 2 it's a 2-dimensional vector space. There are 2 of them, and that corresponds to plus minus signs. So what are these? These are the simultaneous eigenfunctions of L squared, S squared, J squared, and JZ. These are the eigenkets you would observe as the eigenkets of your total spin. If your device was not sensitive to the spin of the electron or the angular momentum, you could only detect the sum of the 2. If your device could only see that, these are the eigenkets that would be relevant to your physics. Questions? All right, so this is the end of this lecture. What did we do? We built a formal theory. So in the last lecture, we just wrote how we talked about what the hell is the additional angular momentum. Why does it matter? Because there are 2 choices of bases, and there's physics of it that has to do with whether what eigenkets are more natural, which observables can you actually observe, right? There are 2 choices, and the basis that takes you between the 2 are called Clebsch-Gordon coefficients. We started with the example of 2 spins. Then today we did a formal theory of adding angular momenta, whatever they may be. We worked out, we told you how to derive the Clebsch-Gordon coefficients. Last time I just wrote them down on the board. Now you know how to do it. It's a little bit calculationally involved, but straightforward. These are all matrix diagonalizations. We're not seeing it that way, but it's nothing like that, except for that. And then we worked out an example of an electron with angular momentum orbiting a nucleus and found as an example. All right, are there any last questions? We have one lecture left of the angular momentum discussion. In the next lecture, what we're gonna present you guys is another way of formulating angular momentum due to Schrödinger, which simplifies your life quite a lot. So these calculations become a lot simpler. Now, why didn't we present this at first? Because it's more sophisticated conceptually. And it's a little bit deeper in group theory, but you see the result, how easily it works out. And then I'll finish with a discussion on direct sums. There will be 2 last lectures left. And during those lectures, we'll discuss conservation laws. Angular momentum was important in this whole discussion because it commuted with Hamiltonian, right? Because we looked at spherically symmetric potentials, right? We're gonna describe why does that matter, what is the story, and then if we have time, I don't know if we will have time, parity and time reversal, we'll talk about discrete symmetries, and I'll try to give you an idea of how to think about quantum mechanics a little bit more abstractly. How did people come up with this kind of stuff to start with? All right, any last questions? If not, thank you. Oh, one little comment, sorry. I unfortunately have to run. I have a Zoom call I cannot not attend. But if you want to come to the office hours, it's perfectly fine, but